In this video, I'm going to show you how to calculate velocity from data that you've collected from a cart or something sliding down a ramp. So the first question is, does this equation work? Position equals velocity times time plus initial position. If we want to calculate the velocity for this cart as it rolls down the ramp, one thing you may notice is there is not a one velocity for the cart. There is no the velocity for the cart. So this does not work. What velocity is it going to give us? Because this velocity is increasing. It's going faster and faster and faster. And this equation will give you one velocity. So it's not going to work. So why not? It's speeding up the entire time. That model is only for constant velocity. So if you don't have a constant velocity motion, you throw that equation out. It will not model the motion, only if it's constant velocity. So would our answer be better if we looked at a shorter time interval? So for instance, we had the cart roll all the way down the ramp, and here it's going pretty slow, and here it's going really fast. And so if we looked at a shorter time interval, there wouldn't be as much time for it to change its velocity. So our answer would be less bad. I wouldn't say the answer would be better. It would be less bad if we use a shorter time interval, because the cart isn't going to speed up as much if it's going maybe only half the time, or this would be half the distance. So yes, it's slightly better. It's not exact, but it is better because there's less time to speed up. How could we make our answer even better? Well, we could use a shorter time interval. And so what we're going to do, instead of calculating the time interval for all the way down the ramp, instead of half the ramp, we're going to use a shorter time interval, maybe just from here to here. So that answer would be better. There's less time to speed up. How could we make our answer even better? So this equation is not working well. It's giving an approximate velocity, and we are using shorter and shorter time intervals because this equation only gives us one velocity. And so this thing has a bunch of different velocities, but if we use a shorter time interval, then their velocity doesn't change as much. And so your one velocity that this equation gives you is going to be a little closer to something we're looking for. So what can we do? We can make it shorter. So we're just going to make it shorter and shorter and shorter and shorter and shorter. If you've done limits in calculus, there's a connection here. So to get velocity versus time data, we need to calculate the approximate velocity over a bunch of really short time intervals as it rolls down the ramp. This is actually the average velocity over each of those time intervals. So how to do this mathematically? Your data is going to look something like this. You're going to have a bunch of positions, and you're going to have a bunch of times here. Hopefully your times are in equal intervals. There's nothing, it'll make your life a lot easier. So what we're going to do is we're going to calculate here, 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 each one of those points. So we're going to use our constant velocity equation. Now, we are kind of abusing this. It's not really correct to use a constant velocity equation to model something that has a changing velocity. But because we're doing short time intervals, it's going to be close enough. Now, we're going to use this equation over this short little time interval here, this equation over this short time interval here, over there, over there, over there, over and over and over again. So we're going to get the approximate velocity over this time interval, the approximate velocity over this time interval, and so on and so forth. So then we will have a bunch of different velocities as it goes down the ramp. So whenever you're using the same equation over and over and over again, solve it for the variable you're looking for with just variables. So if we solve this equation for velocity, move x naught, or initial position, over to the other side, divide both sides by time. Now this time here, this is the time interval. It's not the time on your stopwatch. It's the interval that it takes to go from your starting position to your final position for that time interval. So it's the time it takes to go from here to here, time it takes to go from here to here, time it takes to go from here to here, so on and so forth. So it's the time interval. Now, for this first segment here, we started at a position of 0, went to position 0.06 meters. Our x minus x naught, the top part of the equation, is just going, we're going to get it from these two data points. And the time interval, or t minus t naught, is just the difference between these two. So our equation would look like this. We'd find the difference between those 2 points, and the difference between those 2 points, and we'd divide them, and that would give us our average velocity over that time, or the approximate velocity over that very short time interval. And then we do it again for the next two. We'd say, okay, now you went from 0.06 meters to 0.15 meters. And how long did it take? Notice these time intervals are the same, so we really don't have to do this calculation every time. It's just 0.1 seconds with this data here. So if you have the same time intervals, this will make it very easy. And so we do the same thing. And then we rinse and repeat, rinse and repeat. So we're just asking over this short period of time, how long did it take? That's our denominator. How far did it go? That's our numerator. That's going to give us our average velocity over that time. And we do that over and over again, and we have these velocities. Now, it's technically not correct to put this velocity right here with this time, but this is just an approximation. It's going to be close enough. So on your data table, you would put here for this, the first velocity 0, the second velocity would be the first answer you'd calculate, the next one would be the next one. You can do this with the calculated column and pivot, and so you don't have to do any of this on a calculator. You basically just make a calculated column, and you're going to do find the difference between these two, or you may need to do it on a calculator, I forget. But this should not take you very long, especially if you have equal time intervals. Now, there's a connection here. Some of you may be seeing that I want to show you. How does this connect to the graph? So we did this mathematically, took this equation that's for constant velocity, and we used it over very short intervals to give us approximate velocities over each of those short intervals. But what we're also doing here is we're finding the slope of a position versus time graph. Slope of a position versus time graph gives us the velocity. So if we pick 2 points, so maybe this is this point here to this point here on this graph. So this is going to be my x, and this is going to be my x naught. So this point here is my x naught, and this point here is my x. And here, this sort of vertical distance on the graph, that's x minus x naught. That would just be, the difference between those 2 points. How far did it go? And then the time would be the difference between these 2 points right here. How much time did it take to go this far? And you may notice that x minus x naught and t minus t naught, this right here is your numerator, that's your rise, and this right here is your denominator, that's your run. You're just doing rise over run. We are just doing rise over run. So if we do it this way, rise over run, rise over run, rise over run, that is just slope. You're just calculating the slope. Now notice this makes it very clear why this is an approximation. The slope of this curve is a million different slopes. It's not one slope, but this is the average slope, or this is the slope right smack dab in the middle of that time interval. So it's not perfect, but it's close enough. So what we do is we do this over really short time intervals, and I find the slope from here to here. I find the slope from here to here. I find the slope from here to here, so on and so forth. So I have 1, 2, 3, 4 different velocities now that I can graph. So we approach this mathematically to start with this method, but really it's the same exact as the graphical approach. You can use either approach. You can find a bunch of slopes using a graph, or you can find a bunch of slopes using the equation, and it's the same